This lecture we shall discuss about the main concept of what do we mean by the reaction mechanism. We shall see about what do we mean by the electrophile and what do we mean by the nucleophile and how can we identify an electrophile and a nucleophile, right? So firstly we shall study about what do we mean by the mechanism of a reaction, right? So mechanism of a reaction is the sequence of bond breaking and bond making steps and the energetics of these steps in proceeding from reactants to products. So what do we mean by energetics? Energetics mean the changes in energy, right? So once you are starting with the reactants, in order to convert the reactant into product, you have to increase the energy of the reactant to a certain point, right? So that point of maximum energy of the reactor before it's getting converted into product, right? So this is known as the activation energy. So if the activation energy, which is the energy barrier for the reactants to get converted into the product, so if this energy barrier is very high, then in that case the reaction gets slower. So you have to give some input of energy for the reactants to get converted into product. But in case if this energy barrier is low, it's very easier for the reactants to get converted into product. So the energy changes that take place when you convert the reactant into product, so these energy changes are known as energetics for those reactions, right? So the mechanism of a reaction, it is mainly concerned with number one, the sequence of bond breaking and bond making, and secondly it is concerned with the energetics of each step when a reactant is being converted into product. So there are thousands of organic reactions, such as about esterification, about saponification, about imide formation, addition, elimination, etc. But on the basis of the mechanism of these reactions, these thousands of reactions can be grouped together in a relatively small number of generalized mechanisms, right? So whatever be the general mechanism, whatever be the mechanism, whatever be the reaction, just remember that all type of reactions involve making and breaking of bonds. All bonds consist of electrons. Therefore, the making and breaking of bond will involve movement of electrons, right? So when electrons get paired up, a bond is formed, and when these electrons get separated, then the bond is broken, right? So whenever you are talking about the bond, just remember that we are talking about the electrons, right? So when we say the mechanism, so mechanism is sequence of making and breaking of bond, so it means the mechanisms involve the movement of electrons. So we are seeing the sequence of the movement of electrons when we are considering the mechanism of the reaction. And most of the times when we are considering about the movement of electrons, the electrons move in the form of electron pairs, right? Sometimes the electron move as single electron, but most of the times in mechanisms the electron are involved as electron pair, right? So when we represent the movement of electrons, this representation of movement of electron is known as electron pushing. So this electron pushing is represented by a curved arrow, and the direction of curved arrow is always from electron rich atom or group of atoms to electron deficient atom or group of atom, right? So the origin of this arrow is showing the source of electrons, right? The source of electron is a place or the atom at which electronic density is higher, and the destination of this arrow means the head of this arrow will point towards an atom which is electronically deficient, right? So the electron pushing arrow is represented by a curved arrow, and the direction of this curved arrow is always from the rich atom to atom which is deficient in electrons. So in general, the organic mechanisms are classified into three categories. Number one, the ionic mechanism or the polar reaction mechanism. Second, the pericyclic reaction mechanisms, and thirdly, the free radical mechanisms. So what do we mean by the ionic or polar mechanism? ionic or polar mechanisms are the reaction mechanisms that involve the heterolytic cleavage of bond, right? So what do we mean by heterolytic cleavage of a bond? Let's consider that if you have a bond between atom A and B, right? Now we have to break this bond, right? So there are two possibilities by which we can break this bond. The first possibility is that, so you know that each bond is consisting of two electrons. So one electron is here and one electron is here, right? So one possibility of the bond breakage is that bond breaks in such a way that both of the atoms get one electron each. So one electron goes to this atom B and one electron goes to this atom A, right? So as a result of this bond breakage, what we get an A with unpaired electron, and we get a B also with an unpaired electron, right? So this bond breakage has occurred in this way that both of the atoms are getting equal number of electrons. So such type of bond breakage is known as homolytic cleavage, right? So this is known as homolytic cleavage, right? So cleavage means bond breakage and homo means same, lytic means lysis, means breakdown. So such bond breakage in which both atoms get one electron each, this is known as homolytic cleavage. And these species with unpaired electrons, these species are known as free radicals, right? So whenever we get free radicals, whenever we break a bond in such a way that both atoms get one electron each, then we get free radicals, and such mechanisms are known as free radical reaction mechanisms, right? So whenever you are showing a free radical mechanism, always remember that we use the arrow which is a Fishhook arrow. Fishhook arrow is an arrow which is single-headed arrow, right? So this arrow is showing movement of one electron, right? So in the previous slide I showed that the point of starting of this arrow is the point where electronic density is higher. So electronic density is higher between the bond, and this arrowhead is pointing towards the atom which will gain the electron, right? So in this case, the Fishhook arrow has its origin at this electron and the head is on B. So this B is gaining the electron like here, right? So in this case, this mechanism which involves formation of free radicals, this mechanism is known as free radical reaction mechanism. Well, another possibility is here that we are having a bond between A and B right here. So again, so this bond is consisting of two electrons, one electron here, one electron here. So when we are considering the bond breakage, now in this case it so happens that one of the atom gets both electrons while the other atom does not get any electron, right? So in this specific case, what we get an A. So A does not get any electrons, so A is becoming deficient, while the B has got both of the electrons, so the B has got a negative charge. So this type of bond cleavage in which both atoms get different number of electrons, so one atom is getting both electron while other is not getting any type of electrons, right? So this type of bond cleavage is known as heterolytic bond cleavage, right? So this heterolytic bond cleavage, results in formation of a species which is positively charged. So you know that positively charged species are known as cation, while we get a negatively charged species which is known as anion, right? So reaction mechanisms in which we get a cation or anion, such reaction mechanisms are known as ionic or polar reaction mechanisms, right? So whenever in any reaction, when you see this generation of positive charge and a negative charge, just keep in mind this reaction mechanism is ionic reaction mechanism or polar reaction mechanism. And whenever you are considering a reaction mechanism where there is generation of free radicals, remember this is homolytic cleavage and the reaction mechanism is free radical reaction mechanism. Well, we have a third type of reaction mechanism known as pericyclic reaction mechanism. So you shall study pericyclic reaction mechanism in future in the upcoming lectures. So in case of pericyclic reactions, there is no polar mechanism involved, so there is no formation of carbocation, carbanion, and there is no formation of free radical as well. Right? These reactions are a bit different. So the basic thing about pericyclic reaction is that these are concerted reactions, right? These are single step reactions, and the most important thing is that these reactions involve formation of a cyclic transition state. Right? So all of the pericyclic reactions, they have two things in common. Number one, all of these reactions are concerted, means they are taking place in a single step, and all of these involve formation of a cyclic transition state. Right? So this is about the type of reaction mechanism, right? So we have ionic reaction mechanisms. Ionic reaction mechanism are also known as polar reaction mechanism. Important thing is that these involve formation of a carbocation and carbanion, and these involve the heterolytic bond cleavage. While in case of the free radical mechanisms, the free radical mechanism involve formation of free radicals, and these involve the homolytic bond cleavage. Right? So in this lecture, we will be only concerned with this ionic reaction mechanism. Right? So in case of ionic reaction mechanism, right, so in order to understand these ionic reaction mechanisms, we need to be able to recognize whether a particular reagent will accept an electron pair or it will donate an electron pair. Right, so in heterolytic cleavage, you saw that one of the atoms was accepting an electron pair, so it was accepting 2 electrons, while the other was not gaining any electrons each. Right, so whenever you are considering with this ionic reaction mechanism, you must know that which of the atom or which of the group will accept the electron pair and which of the group will donate an electron pair. Right, so reagents that accept electron pair are called electrophile. Right, so any species that can accept an electron pair is known as electrophile. Right, electro means electron and phile means loving. So anything which has love for electron, which has affinity for electron, which attracts the electron to itself, such a reagent is known as electrophile. Right, so we know that the electrophiles are electron pair acceptor, means they are going to accept the electron pair. Right, and we also know that these are known as the Lewis acid. So any species that can accept an electron pair is known as Lewis acid. Therefore, all electrophiles are Lewis acids. Right, so just from the basic inorganic chemistry which we have studied in the last semester, so we know that the Lewis acids are electron pair acceptors. The same definition applies on electrophile as well. Right, so therefore all electrophiles are Lewis acids, or you can say all Lewis acids are electrophiles. Right, so from this definition it's very clear that all carbocations, also known as carbonium ions, are electrophiles because they have a full positive charge and they are highly deficient, and they need 2 electrons. Right, so since they need 2 electrons, so they can easily accept 2 electrons. So since they are accepting 2 electrons, mean they are accepting electron pair, therefore they are considered as electrophile, or they are also known as Lewis acids. Right, so since they are electronically deficient, therefore they tend to form bond with electronically rich species. Right, so if there is a deficiency, it's natural for the deficient center to seek something which is electronically rich. Right, so electrophiles, they are electronically deficient. Right, that's why they are accepting the electron pair. Since they are electronically deficient, so they are attracted towards something which is electronically rich. Right, so whenever you have to justify whether a species will be electrophile or not, the general thing is that if any species has a partially positive charge, right, so any partially positive species is definitely bonded to an electronegative atom, then such a species is electronically deficient. right? Since electronically deficient, therefore it will act as an electrophile, right? So whenever you see any species which is partially positive, then that will be definitely an electrophile. If you see any species which is fully positive charge, definitely that will be an electrophile. Third condition is that members of group 3A, that's the boron family. So you know that the members of group 3A, they are considered as electron deficient. Why they are considering electron deficient? Because they cannot complete their outermost shell. So their outermost shell is incomplete. So no matter what they do, they cannot complete the outermost shell. So from coordinate covalent bond formation, you have studied that the members of group 3A, they form the coordinate covalent bond because they cannot complete the outermost shell. For the same reason, the group members of 3A, they act as electrophiles because they want to accept an electron pair, right? So whenever you want to check whether a species is electrophile or not, so you have three criterions. Number one criterion, if any species has a full positive charge, that will definitely act as an electrophile. If a species has a partial positive charge because of its bonding with an electronegative atom, then in that case it will act as an electrophile. And the third criterion is that if any atom is belonging to group number 3A, that is the boron family, then in that case that will act as an electrophile, or that will act as a Lewis acid. So let's consider a few examples in which we can see whether a species will act as electrophile or not. So firstly, so we have here a carbonyl system. So here we have a ketone here. So you know that this is carbon, and this carbon is bonded with an oxygen, right? So oxygen is an electronegative atom, right? So this oxygen is pulling the electronic density from the carbon. So carbon is becoming partially positive. So by means of resonance, we can show like that. So when we show the resonance structure for this carbonyl, we know that carbon is positive and oxygen is negative. So here you can see carbon is positively charged, right? So carbon is deficient here, right? So because carbon is deficient, so this carbon will act as an electrophile. Now we have a chlorine here. So if you can show the London dispersion forces or the van der Waals forces here, so because of the dispersion, the London dispersion forces, you know, because of the instantaneous dipole, so one of the chlorine becomes partially positive while the other chlorine becomes partially negative, right? So here this chlorine, which is partially positive at this instant, so this chlorine will act as an electrophile. So here, because of partial positive charge, the chlorine is acting as an electrophile. So here we have a methyl chloride. So here you can see carbon is bonded with an electronegative atom, which is chlorine. So here carbon is partially positive, right? So because carbon is partially positive, so carbon will act as an electrophile here. It will attract electronic density because it is deficient here. Now we have an HCl. So you know that because of an HCl, so here the HCl dissociates from H positive ion. So here H positive is highly electronically deficient because it has lost its electrons, so it can get 2 electrons, right? So this hydrogen wants to get 2 electrons, so it can accept 2 electrons, therefore it is an electrophile here. Here we have a nitrite ion. So in case there is an H missing, right? So please put in H here, right? So this nitric acid in presence of sulfuric acid, when it reacts together, so we get a nitronium ion here. So you can see the nitrogen here is positively charged, right? So this nitrogen, with it positively charged, it will act as an electrophile, right? So here you have seen the 2 criterion. So if whenever an atom is positive or when an atom is partially positive, so in both of these cases it will act as an electrophile. So let's consider a few more examples, right? So know that electrophiles are also known as Lewis acids. So whenever someone says Lewis acids, just keep in mind that the thing is about an electrophilic species. So here we have carbon, which is positively charged here, right, with full positive is an electrophile. So here we have boron here, right? So boron is member of group 3A. So here it is electronically deficient here. So boron or any member of boron family such as aluminium, indium, gallium, thallium, so all of these are electronically deficient. So both of these are member of group 3A, so they are electronically deficient and they will act as Lewis acid. So whenever you see the member of group 3A, just keep in mind that these will act as electrophile. Now we have another group. So here you can see a sulfur, which is central atom, and the sulfur is attached with 4 oxygens here, right? So because it is attached to 4 oxygens, oxygen is electronegative, so they are pulling the electronic density from the sulfur. So sulfur is here deficient. So sulfur is an electrophile here, right, because it is deficient. Further, so these hydrogens are also electronically deficient, right? So this hydrogen is also an electrophile. Also sulfur is acting as an electrophile here. So whenever you see something which is deficient, whether that is because of the appearance of a full positive charge, or whether there is appearance of a partial positive charge, or whether you see a member of group 3A, then just make sure whatever you are talking about, you're talking about an electrophile here. So just for example, so here we have H positive ion, you can say full positive charge, so that's an electrophile. So here we have CO2, carbon dioxide. So this carbon dioxide, this carbon which is central is partially positive, so this carbon is electrophile, right? We are not saying carbon dioxide is electrophile, we are saying this carbon is electrophile here, right? So whenever any electronically rich species attached or available, then this carbon will react with this rich species. So these oxygens are electronically rich, but this carbon is deficient here. So here we have an aldehydic functional group. You can see this carbon is partially positive, right? So this carbon is deficient, right? So just remember, it is not a molecule which is electrophile. It is the atom or group of atoms which is acting as an electrophile. So this carbonyl carbon here, this carbonyl carbon is acting as an electrophile here. Similarly, we have an ester functional group here. This carbon is also acting as an electrophile here. And here we have a methyl chloride. So because this carbon is attached directly with the chlorine, so chlorine is pulling the electronic density toward itself, so this carbon is becoming deficient, so this carbon is acting as an electrophile, right? So whenever you see a certain structure, and whenever you have to see whether the structure has a partial positive, partial or full positive charge, or if the structure has a electron deficient atom of group 3A, just remember that this species will act as an electrophile here. Now we have reagents that are capable of donating an electron pair, right? So whenever you see a reagent that is an electron pair or that can donate an electron pair, just remember that is electronically rich, and such a species is known as a nucleophile, right? So nucleo means nucleus and phile mean loving. So nucleus has a positive charge here. It means that any species that can donate an electron, that will be attracted towards a positive charge, right? So the nucleophilic species are electronically rich, and they are attracted towards species which are electronically deficient. All nucleophiles are electron pair donors, and you know that electron pair donors are known as Lewis bases. Therefore, all nucleophiles are Lewis bases, right? So whenever you want to see whether a species will act as a Lewis base or a nucleophile or not, just remember, whenever you see a full negative charge, whenever you see a partial negative charge, or whenever you see an atom with a lone pair, just remember that species will act as a nucleophile, right? So here we have drawn the conclusion that whenever you are seeing about a species which is nucleophile, it must be either partially negative, it must have a full negative charge, or it must have a lone pair, right? So carbanions, so they have a full negative charge. It is understood they are acting as a nucleophile. Also remember, all nucleophiles are Lewis bases because they are electron pair donors, right? So it's important to note that all reagents that you will be using in the reaction chemistry, so all reagents are composed of a partial positive charge and a partial negative end, right? So all reagents are composed of an electrophilic part and a nucleophilic part. We shall identify which part will act as electrophile and which part will act as a nucleophile. Right, so by just observing the charge on an atom or group of atom, we can easily classify the reagent or species as a nucleophile or an electrophile. So any positively charged atom will be electrophile, any negatively charged atom will be considered as a nucleophile. That's very easy. So positive charge, electrophile, negative charge, nucleophile. However, there's sometimes reagents that are overall electronically neutral. For example, water. So in such cases, how can we determine the species will be nucleophile or electrophile, right? The electronic factors, the electronic effect that include the inductive effect and resonance effect, that will help determine whether the atom or group of atom will act as electrophile or nucleophile, right? So just have a clear revision or clear thinking of the inductive effect and resonance effect in your mind when you're considering about the reaction mechanisms. So here we are considering the system which can act as nucleophile. Number one, we will consider about anions, means the negatively charged species. So we have Br negative, we have OH negative, and we have Cn negative. So here negative charge is on carbon. So any species that has a full negative charge, that will act as a nucleophile. Second, any species that is partially negative, that will also act as a nucleophile. Any species that has a pi bond, right? So any species that has a pi bond can act as a nucleophile, right? So it is normally considered that pi bond should be between carbon and carbon, especially when you're considering about the organic reactions, right? So whenever you see a pi bond between carbon-carbon, whether that's a double bond, there is a triple bond, whether that's a pi bond of a benzene ring, just remember this pi bond is electronically rich, and this pi bond will act as a nucleophile. The third condition is that atom is a lone pair. So you know that atoms from group number 5, group number 6, and group number 7. So all of these elements of these groups, they have lone pairs. So the group number 5, which is nitrogen family, these have one lone pairs. The members of group number 6, that's oxygen family, they have 2 lone pairs, and the members of group 7, which are halogens, they have 3 lone pairs. So whenever you see an atom with lone pair, just keep in mind this atom can act as a nucleophile, right? So in case of water, since the central atom, which is oxygen, it has 2 lone pairs, that's why this oxygen will act as nucleophile. Similarly, nitrogen will act as nucleophile. So here this oxygen will act as a nucleophile, but this carbon will act as electrophile, because this carbon is deficient, this oxygen is rich, right? So here you can see this is a system which has an electrophilic center, because this carbon is deficient, and here we have a nucleophilic center as well, because this oxygen is electronically rich. Again, so we have an iodide ion. So iodide has a formal negative charge, right? So because of that full negative charge, formal negative charge, so this iodide will act as a nucleophile. Here we have a methyl magnesium bromide, right? So we have a methyl. So methyl is negatively charged, while magnesium is positively charged, right? So the methyl fragment of this reagent, since that is negatively charged, so that will be a nucleophile, while this magnesium, which is deficient, will be electrophile, right? So here we have a pi bond in isobutylene, because the pi bond, this pi bond will act as electron pair donors, and that will act as a nucleophile here. Here we have ammonia, so it's ammonia with nitrogen with a lone pair, so this will also act as a nucleophile. So now let's identify electrophiles and nucleophiles in certain reactions here, right? So here we have a substrate. So in this substrate you can see this carbon is bonded with a bromine. So bromine is electronegative. So bromine is pulling the electronic density toward itself. So since bromine is pulling electronic density from the carbon, so carbon is becoming electronically deficient. So since electronically deficient, so that's why this carbon is electrophile, right? This is electrophilic atom. while here we have a hydroxyl ion. So you can see hydroxyl ion has extra electrons, it is electronically rich. So the hydroxyl ion, the oxygen atom is a nucleophile, right? So always remember, nucleophile will always attack on electrophile, right? So this is direction of arrow. You can see this is rich center and this is deficient center, right? So this arrow is showing the electron pulling mechanism, right? So the arrow is always from efficient to deficient. So this atom is electronically rich, so the source of electrons is this rich atom, and the destination of the arrow will be the atom which is electronically deficient, right? So in this reaction we can easily identify which is electrophile and which is nucleophile. So this system which is electronically rich, this is nucleophile, and this carbon is an electrophile here, right? Again we have another example. So here we have a isobutyl, we have tertiary butyl group. So here we have a tertiary butyl carbocations. So this carbon is having a full positive charge, right? With full positive charge, this will be considered as an electrophile. So this carbon is electrophilic. Here we have an oxygen. So oxygen has lone pairs, right? So this oxygen is donating electron pairs. See the direction of arrow, this is from rich to deficient, right? So here this water, oxygen of this water molecule, this oxygen is acting as a nucleophile, while this carbon which is full positive charge is acting as an electrophile here. We have in HCl, you can see this hydroxyl ion. So this oxygen is a negative, so oxygen is nucleophile, right? And this hydrogen is partially positive, so this partially positive hydrogen is an electrophile. Similarly, we have chlorine which is positively charged, so full positive, it means chlorine is electrophile. And here we have a benzene ring. The electronic density of the benzene is electronically rich. So this pi bond of the benzene will act as a nucleophile, and this chlorine which is positively charged will act as electrophile here, right? Again we have the same example here. So this is a nucleophile and that's an electrophile here. Guys, I hope so you have understood about the electrophile and nucleophile, and whenever you see a reagent and whenever you have to decide whether the reagent or the part of reagent will act as electrophile or not, just see whether it has a positive charge, it has partial positive charge or not, right? Or so in these cases it will act as electrophile, or in case if there is an electron deficient atom attached as a central atom, then in that case the species will act as an electrophile. But whenever there is a pi bond between carbon and carbon, whether that's a double bond or triple bond, or whenever there is a full negative charge, or whether there is a partial negative charge, or whether there is an atom with a lone pair, in all of these cases the species will act as a nucleophile. So just for seeing the overall difference in electrophile and a nucleophile here. So electrophile is an atom or a molecule or group of atoms that can accept an electron pair, while a nucleophile is an atom or a group of atoms or a molecule that can donate electron pairs, right? So there's a difference in electron acceptance or electron donation. So any species that can accept electron pair, that's what we call electrophile, and a species that can donate electron pair, that will be considered as a nucleophile, right? So electrophiles can be either positively charged, it can be full positive, or it can be full negative, for partially positive or full positive charge, or they can be neutral, right? So nucleophiles can be either fully negatively charged or partially negatively charged, or they can be neutral, right? So the electrophiles undergo electrophilic addition or electrophilic substitution reactions. Similarly, nucleophiles also undergo nucleophilic addition or nucleophilic substitution reactions, right? So all electrophiles are known as Lewis acids and all nucleophiles are known as Lewis bases. I hope you have understood this lecture well. So that's the end of the lecture. Thank you for your patience.